In this first presentation, we are going to analyze the complexity of modeling multiphase displacement in natural porous media. The objective is to analyze the impact of different variables on the movement of fluids in the reservoir. In particular, the impact of fluid saturation, the driving forces, and the displacement's geometry. As an example, we will use the oil-water relative permeability curves, but the analysis are totally valid for the simultaneous flow of any set of immiscible fluids in the same porous medium. Those of us who work in reservoir engineering are familiar with the relative permeability curves, which in the case of water-oil systems show relative permeability to oil and relative permeability to water as a function of the water saturation between the saturation extremes, defined by the irreducible water saturation value, and the residual oil saturation in the system. We usually say that these curves represent the flow rate capacity of each of the modeled phases, relative to the absolute flow rate capacity of the system, which is determined when just a single phase is flowing through it. A fundamental characteristic of these curves is that they depend only on the water saturation, although it is not explicitly indicated. It should be remembered that these curves do not depend on flow rates, nor on displacement times involved in the displacement, nor on flow geometry, nor on viscosity ratio, nor on other variables that we will consider on subsequent talks. Basically, these curves are born from Darcy's law, which for linear flow takes the form we are looking at. In general, the variable that interests us, as reservoir engineers, is the flow rate. And in the single-phase case, water for example, the rate depends on a geometric factor that, in linear flow, involves the area and the length of the system, and on the fluid used, modeled through its viscosity, the displacement conditions, and a property, precisely defined through this equation, named permeability of the porous medium, which does not depend on the other variables. It is an intrinsic property of every porous medium. When this law is adapted to multiphase flow, it is split in such a way that it allows modeling the water and oil rates separately, which are the unknowns that interest us in the case we are analyzing. For this, each of the previously mentioned variables, which are specific to each phase, adopts their corresponding values. And a correction factor is added in the form of relative permeability curves to water and oil that depend, as already mentioned, only on the water saturation. Although it is trivial, it should be mentioned that for the water or oil flow rates to be zero, at the production end, does not necessarily implies the absence of this phase in the porous medium, but that the corresponding relative permeability takes zero value. Yet, easy as they are to define, these curves have given rise to numerous conceptual problems throughout the history of reservoir engineering. This is stated by several prominent authors, such as Dake and specialists who have worked on the subject. In Dake's case, when he explains multiphase flow modeling in his second book, The Practice of Reservoir Engineering, he includes some striking concepts. On one hand, he mentions a great veneration for relative permeability curves. Although veneration is not a term commonly applied in technical developments, this word makes sense in the context where Dake explains the relationship between reservoir engineering and curves modeling multiphase flow. Later we find a second very striking paragraph where he indicates that the expected hierarchy of variables for reservoir characterization is reversed. Instead of being one more variable, subject to all the regular controls and checks, Dake states that the rel-perm curves are assumed to be intrinsically correct. In consequence, all the rest of the variables and models are arranged around these curves. Walter Rose is an author, possibly less known than Dake, who in 1999 presented a kind of technical autobiography relating 50 years of personal history devoted to work in reservoir engineering and specifically in the generation, modeling and use of rel-perm curves. In his work he makes a series of very remarkable reflections. For example, he states that in year 99, the rel-perm curves are still subject to interpretations that change over time and cause perplexity among those who use them. There is another, even more striking, paragraph where he states something too basic to deserve a special mention. According to Rose, it is still necessary to include, as a fundamental point of study, the need to understand how to measure and apply relative permeability data. We are talking about a person who for 50 years dedicated himself to generate and use these data and, at that moment, is saying that it is still necessary to understand how to measure and apply them for modeling reservoir transport phenomena. We will see later that the word transport instead of production is not trivial in the regular use of rel-perm curves. Let's see how the rel-perm curves are obtained. Basically, these curves are obtained in the laboratory on what we call plugs or cylindrical samples, which are extracted from the reservoir, and the simplest and most widely used method is the non-stationary one. The laboratory sample has typically 1.5 inches in diameter, about 4 centimeters, and is between 2 and 3 inches long, about 6 or 7 centimeters. From this moment on, we are going to represent it schematically as a rectangle where its color indicates irreducible water conditions, where the only mobile phase is oil. We are using the water-oil relative permeabilities as a general example of multiphase displacement. This sample is laterally confined in a measurement cell, in such a way that only one fluid inlet face and one fluid outlet face are exposed. During the test, water is injected, and water and oil are produced through the outlet face, until residual oil conditions are reached. At that stage only water is produced and the system reaches steady state where the same amount of water that enters the plug leaves through the outlet face. In summary, emulating the history of the producing reservoirs, we start from a system with maximum oil saturation, generally under conditions of irreducible water, and at the end of the lab test, residual oil conditions are reached. During the test, the water and oil production rates are measured at the production end, which is historically identified as phase 2. This nomenclature will be used in later presentations. When the flow equations are solved under explicit conditions, the frontal advance theory is used. Let us analyze, then, different possible displacements, in the same media, controlled by the different forces that operate at the reservoir level. Let's start with the so-called viscous forces, the external forces that we apply to displacements, in the reservoir or in the laboratory. In this example, we start with the case with mobility ratio near 1. This means that water is about as mobile as oil. Under this condition, the phase that pushes the flow through the porous medium develops similar flow rate than the displaced phase, leading to what is known as piston-like displacement. In these conditions, what we know as viscous fingering occurs, although the phenomenon is limited. At the time represented in the image, we are only injecting water through the inlet face and only oil is being produced through the outlet face, since the water has not yet reached the production end. However, if mobility increases, that is, if water is more mobile than oil, typically with a more viscous oil, the viscous fingering phenomenon is more pronounced and, in this way, a scenario is reached where the same amount of water in the porous medium leads to water being produced at the outlet end. If the water mobility is much higher, with an even more viscous oil, the phenomenon is even more pronounced and, with the same water saturation, the water rate increases at the production end. Consequently, we are seeing three possible scenarios, with the same average system water saturation, in which the water production rate noticeably differs at the production end. In the first case the water flow rate is 0. In the second case it is greater than the first one because some water is produced. And in the third case it is even higher than in the second case. Another way to generate the displacement of oil with water is not through rel-perm experiments but through imbibition phenomena. Let's first see what we denominate partial immersion. This is the same system we analyzed previously. Only that, in this case, we put it in contact with a water source in such a way that only the lower end is immersed. Under these conditions, the ingress of water occurs only through the contact area. This leads to the fact that, When the aqueous phase enters the porous medium, oil is produced by the area that is not wetted by water. In particular, the one that interests us is the upper face or outlet face, which is the one that we are following through the different experiments. When the water saturation reaches 50%, the image shows the conditions that the sample is in. One characteristic that should be highlighted is that, when the displacement of oil with water is caused by imbibition phenomena, a simple volumetric balance is maintained, that is, for each volume of water that enters the sample, one volume of oil is produced, neither more nor less. The second scenario that we will consider for the same system, again under the almost exclusive domain of capillary forces, is with the sample totally immersed in water. In this case, the water has the possibility to enter the sample through all the faces, and therefore oil production is also produced by all wetted faces of the sample, including the face we are analyzing, the upper face in this picture. When we reach the conditions shown in the image, the average sample water saturation is, again, 50%. Comparing this displacement with the previous examples we analyzed, we can see that, in this case, the top face is producing oil with a counter-current flow of water. Despite the change in scenario, the basic rule of imbibition processes is still maintained. Displacement occurs with the ratio of one volume to one volume. Finally, we will see what happens when gravitational forces dominate the displacement and rearrangement of fluids. This is an image previously seen and corresponds to a viscous displacement with mobility ratio close to 1. But, if at this time in the experiment, we make a prolonged closure and let the fluids rearrange due to gravitational effects, and then continue water injection, we find the following situation: during the closure the fluids were rearranged, according to their densities, with the highest density phase, water, taking the lower part of the pearl network and the oil phase on top. In this way, when resuming water injection, both phases present themselves at the outlet face, changing the rates ratio that we had in the upper image. But, gravitational rearrangement can produce different results, according to the spatial orientation of the sample or block that we are analyzing. In these three examples we see that, if the same sample and the same fluids are subjected to displacement under the domain of gravitational forces, the behavior of the face that we are following in these cases changes with the orientation of the sample in space. So, grouping all the examples we saw, all three viscous displacements, both imbibition displacements, and the gravitationally dominated displacement, what we can observe is that the flow behavior of the face that we are analyzing at the same sample average water saturation is notoriously different, according to the displacement conditions. In summary, the question that arises is, how can we model the flow capacity of the selected face that we are analyzing, only as a function of water saturation? Taking into account that in all cases the sample average water saturation is 50%. Based on these simple analysis, describing multiphase flow only in terms of water saturation seems like an impossible task. It is evident that there are other variables that also impact the movement of fluids. However, an initial answer is given to this general question, the one that somehow triggered the concept and use of the relative permeability curves in reservoir engineering. It is summarized in this paragraph, arguing that by eliminating two of the three forces that regularly operate at the reservoir level, the fractional flow of water, a distant relative of the relative permeability curves, depends only on the water saturation. This is the foundational work of Buckley and Leverett's forward advance theory, dating back to the year 42. Precisely, the intention of the series that begins with this first presentation on multiphase displacement, aims to analyze the validity and use of this original proposal and other related concepts that have been developed over the years to carry out reservoir modeling.